This video introduces you to the idea of the electrophilic addition mechanism. They show step by step what happens when alkenes undergo addition reactions, specifically looking at the reaction between an alkene and bromine. By the end of the video, you ought to be able to define the term electrophile, addition, and you ought to have a general sense of what's meant by a mechanism in chemistry. In addition, you ought to be able to do the step-by-step sequence of events that happens when an alkene reacts with bromine, showing the movement of electrons with curly arrows and adding in relevant charges. You should already be aware that the typical reaction that alkenes undergo is called addition, and this involves the double bond in the alkene group turning into a single bond, allowing one extra group to bond to each of the carbons that were involved in the alkene group. For the course, you should be aware of four particular reactants that can do addition reactions with alkenes: bromine, hydrogen bromide, hydrogen and water, and be becoming familiar with the reagents and conditions needed for those reactants. If you think about it, this raises the question, though, why do those four substances react with alkenes? Why don't they react with alkanes? And can everything react with alkenes? To explain these things, researchers in the past have come up with this electrophilic addition mechanism that we're going to be learning about in the video. And it specifically explores the bond breaking and the bond forming that goes on during the reactions. Before we dive into the fine detail of this, we'll spend a few moments looking at the words involved here. First of all, the word mechanism. To a chemist, a mechanism simply means the sequence of its steps involved in a reaction that convert reactants into a product. So we're used to looking at a reaction as an overall thing. Here's the reactants, here's the products, but the mechanism looks at what actually happens in between. And of course, this is about bonds breaking and bonds forming. Next, the word electrophilic, and the definition of electrophilic doesn't really help very much. It simply means that the reaction is going to involve an attack by an electrophile, but we obviously need to see what an electrophile means. So brace yourself for one of the slightly longer definitions you'll come across in the chemistry course. What is an electrophile? Well, it's something that can attack and react with organic molecules in a particular way, and there's various parts to the definition. Firstly, we say it's a chemical species. That just means an ion or a molecule with a positive charge on it somewhere. We'll see how that works out in practice as we look through the mechanism. Secondly, it's got to be capable of accepting a pair of electrons. And again, we'll see how that works out during the mechanism. Next, it's going to accept those electrons from a region of high electron density. This is starting to sound a bit obscure, perhaps, but it'll all make sense as we go along. And finally, the effect of accepting those pair of electrons is to form a covalent bond to the organic molecule that the electrophile is attacking. So think of an electrophile as a particle of some kind, an ion, a molecule, whatever, that's going to attack an organic molecule, react with it. So in this case, it's going to be attacking an alkene, and it's got to have these features. It's got to have a positive charge somewhere. It's got to be able to accept a pair of electrons from within the organic molecule a region of high electron density, and the result of that will be that a new covalent bond will form. Addition, hopefully, is a slightly easier term to understand, and you've probably already come across it when talking about the reactions of the alkenes. Addition reactions are simply defined as a reaction in which two or more molecules join to make a single larger molecule, rather like addition in maths, where two or more numbers join to make a larger number. The definition for electrophile mentioned this idea of a region of high electron density, and before we start looking at the step-by-step mechanism, it'll be helpful just to remind ourselves what a double bond between two carbons in an organic molecule actually is. And it's represented here for you. Hopefully you're familiar with this diagram already. It shows the sigma bond, which on its own would be a single bond directly between the two carbon atoms, and then on either side of it this pi bond, the second bond in the double bond. And if you remember, the sigma bond is a relatively strong bond because of significant overlap between the orbitals, the electron orbitals on the two individual carbon atoms, whereas the pi bond is a weaker bond with the lesser overlap of the sort of side to side of the p orbital on each of the two carbon atoms. Now, it's this double bond with its 4 electrons packed into it that gives us our region of high electron density. So this is the thing that's going to be attracting our attacker, the electrophile, in the reaction, and then donating a pair of electrons to it. And specifically, it is the pi bond, it's the 2 electrons in the pi bond that will actually take part in the reaction, because just visually looking at it, you can see they are more exposed to attack by an attacking species. So we're going to start actually looking at the reaction now and the mechanism in practice, this step-by-step sequence of events in the reaction. So here is an alkene, no specific alkene, just showing the double bond between the 2 carbons, and then there would be 2 other things attached to each of the carbons. It really doesn't matter for A-level what those things are. So we're just going to focus in on that double bond between the 2 carbons. And we're going to be looking at the reaction between an alkene group and bromine, Br2, shown here, the Br2 molecule, 2 bromines connected by a single covalent bond. And instantly, considering the definition of an electrophile, we have a problem. The first bit of the definition said that it had a positive charge. And, of course, a bromine molecule doesn't have a charge, it's not an ion. So we need to explore where that positive charge comes from. So I've drawn the 2 molecules now approaching each other, and it's as they get close to each other that we'll see how charge forms on the bromine molecule. The single bond between the 2 bromines is a shared pair of electrons, like any single covalent bond. And if you think about it, we've already said the double bond in the alkene is a region of high electron density. There's 4 electrons packed into that region of space. And as we know, electrons are negative. And so the 4 electrons in the double bond will be repelling the 2 electrons in the single bond in the bromine molecule and repelling them away from the alkene group. The result of this repulsion can be seen in the diagram with the bromine shared pair now down towards the bromine furthest away from the alkene group. Electrons are negative, and so as they move towards one end of the bromine molecule, it creates an imbalance of charge, with the charge where the electrons have moved to being slightly negative. We write slightly negative or partially negative in chemistry with this Greek delta symbol. And so where the electrons have moved towards the bromine furthest away from the alkene group, that becomes partially negative delta minus. Of course, at the other end, that has sort of, to some extent, lost an electron, so it becomes partially positive, and we show that with this delta plus. So we've now caused what's called an induced dipole on the bromine molecule. A dipole meaning it's got sort of 2 electrical poles, a positive end and a negative end, and induced meaning it's been caused by this neighbouring alkene group. The alkene group has produced a dipole on the bromine that wasn't there before. Let's just take a moment then to capture this idea, as you might not have come across it before. So where we see delta plus, delta minus drawn on a molecule or a chemical species, that refers to partial charges, and those are due to unequal sharing of electrons in covalent bonds. They don't actually represent the true formation of ions, rather this unequal sharing, electrons having moved more towards one location and away from another location. On the other hand, of course, we can also have ionic charges in chemistry, the full positive and the full negative, written without the delta symbol. And these are caused when you have truly, fully lost or gained an electron, like a sodium atom. Losing its outer shell electron becomes an Na plus ion. So we now have our Br2 molecule transformed by its proximity to the alkene group into an electrophile, at least matching the beginning of that electrophile definition we encountered, where it's a chemical species with a positive charge. Not necessarily a full ionic charge, a partial positive charge, delta plus, is fine, as you can see here. Now, if you think back to that definition of the electrophile, species with a positive charge that can accept a pair of electrons from a region of high electron density. Well, we've already established that that double bond between the carbons is a region of high electron density. So our electrophile is going to accept a pair of electrons which we draw like this, a curly arrow, perhaps a new exciting feature of your chemistry for you. So we'll pause here for a moment before we carry on with the mechanism, just to explore this idea of the curly arrow. An arrow like this with a full arrowhead on the end shows the movement of a pair of electrons. You might meet later on an arrow with just half a head showing the movement of one electron. But this whole-headed arrow, a movement of a pair of electrons from somewhere to somewhere. And really, as far as you're concerned, there's two places that those pair of electrons could come from, either from a bond, where there's a shared pair in a covalent bond, moving out of that bond somewhere else, which, if you think about it, will break a bond. Or the other source of the pair of electrons could be a lone pair of electrons on an atom. Back to our mechanism then, and we've got this pair of electrons moving from what is actually the pi bond in the carbon-carbon double bond to the space between the carbon atom and the delta plus bromine. Now it's actually showing it moving in the space between the left-hand carbon and the bromine atom. As far as you're concerned, it could go either way. So it could be between the right-hand carbon and the bromine atom. Wouldn't make any difference as far as we're concerned. What it'll be doing, though, is taking that pair of electrons to form a new bond to the bromine atom with the delta plus charge. And of course, bromine can only have one covalent bond, group 7 electrons outer shell. It only needs one shared pair to get the stable 8 in its outer shell. So as a bond forms to the bromine, the existing bonds got to break, and so we see another curly arrow showing the bond between the two bromines breaking, with the shared pair of electrons moving out of that bond. Well, they've got to go somewhere, and they move to the bromine where they've almost fully arrived at anyway, if you think back to the induced dipole. So this diagram now shows the result of those electron pair movements. Take a moment to look at it carefully. At the top, we've got the pair of electrons moving out of the pi bond in the carbon-carbon double bond. And so if you look over on the right in the product, you can see the double bond between the carbons has now turned to a single bond. Where did that electron pair from the alkene pi bond move to? Well, it moved between the left-hand carbon and the bromine, bringing a pair of electrons to create a new bond. And so if you look at the product on the right, we can see now there is a new bond formed from the left-hand carbon to the bromine that was nearest to the alkene group. Moving down, we've got the curly arrow taking a pair of electrons out of the bromine-bromine bond and onto the bromine atom furthest away from the alkene group. And if you look at the product again, you can see now that the bond that was there between the two bromines has gone. As well as breaking and making bonds, the movement of pairs of electrons also is going to cause some changes in charge. So the curved arrow, the curly arrow, takes an electron pair from one place to another place. Now, if you take electrons away from somewhere, you're going to leave some form of positive charge behind. And where the destination is, where you take them to, you're going to be taking negative charge to that destination. So we're going to return to the mechanism and think further about the charge side of things. So returning to our mechanism again and now thinking about charge, think about the alkene group at the top. The shared pair in the pi bond, one of those electrons belonged to the carbon on the left, and it's keeping its share in the new bond with the bromine. So that carbon is unaffected. But the carbon on the right, you could feel a bit sorry for it in these circumstances. One of the electrons in the pi bond originally belonged to it, and that pair of electrons, taking its electron with it, has now gone to form a new bond between the carbon on the left and bromine. So the carbon on the right in the alkene group has effectively had an electron removed from it, and of course removing an electron gives you a full positive ionic charge. Looking at the bromine molecule now, the bond between the two bromines, that also was a shared pair, one electron from each of the two bromines. And that pair of electrons has moved down onto that bottom bromine. Now, one of the electrons already belonged to it, but it's effectively gaining one electron from the other bromine. And so we can mark on that pair of electrons that's arrived and the full ionic negative charge from having gained an electron. So as a result of these electron pair movements, we've both broken bonds, formed bonds, and moved charge around. But note one thing: overall charge is conserved. So on the left-hand side here, we didn't have any overall ionic. We didn't have any ionic charges. On the right, we've now introduced both a 1 plus ionic charge and 1 minus, but of course those also add up to 0. So we've maintained an overall 0 total ionic charge. Here we hit a piece of vocabulary that you need to be familiar with. So just to highlight that, looking at the remains of the alkene group, where we have that carbon atom with the full positive ionic charge on it, that species has a particular name. It's called a carbocation, which you can see written there, pronounced carbocation. Cation generally meaning positive ion, and here on a carbon atom, so carbocation. Going back to our mechanism, the carbocation produced is not a stable thing. We typically say in these organic molecules, carbon always forms 4 bonds. Here it's got 3 covalent bonds and this positive ionic charge. That makes it very prone to being attacked. And lurking around, we have this bromide ion with negative charge that will attract it to the positive carbocation, and also a lone pair of electrons, which could be used to form a bond. And so, as a second step in this mechanism, we now get the lone pair on the bromide ion moving into the space between the carbocation, the positive carbon, and the bromide ion to form a new bond. Of course, as well as bond formation, this is going to have effects on charge. So where the bromide ion, the electron, the arrow is moving away from it, it's going to lose its negative charge, becoming less negative, and the carbon with the positive charge there, where the arrow is moving towards it, it's going to lose its positive charge because negative electron will cancel that out. So the final result of all this movement is exactly what we'd expect from the addition reaction between an alkene and Br2. The double bond has turned to a single bond, the pi bond has gone, that pair of electrons being used to form a new bond between a carbon and one of the bromines from the Br2, and then the other carbon in the alkene group picking up the second bromine with that sort of attack of the bromide ion on the positively charged carbocation. Just to make your life really exciting, and really as a kind of a bit of a stretch on this, there is a second way of looking at this mechanism. The overall result is very similar, but it's called the bromonium version. And let's look at what happens here. So here is our alkene group with the Br2 molecule has moved close, and we've got the induced dipole with the delta plus on the bromine near the alkene group, so set up to be an electrophile. But with the curly arrows, rather than just the pi bond pair of electrons forming one new bond between a carbon and a bromine, we actually have a second curly arrow. Have a look at that. Bromine, of course, has actually got 3 lone pairs on it, if you think about it, and the other, its 7th electron taking part in the shared pair with the other bromine. And one of those lone pairs can also be used to form a bond between the bromine and the other carbon in the alkene group. Of course, this messes with the existing bonding in the Br2, and so just as with the previous version, we get that Br-Br bond breaking with the shared pair of electrons from the single bond between the bromines going on to the bottom bromine. So just have a look at that, see the difference. There's only really the one difference, the one extra curly arrow with the lone pair on the bromine, top bromine atom, forming a bond between one of the carbons and the bromine. So what's the effect of all these electron pairs moving? Well, you can see the product over on the right. We still have down the bottom a bromide ion which has picked up the pair of electrons out of the Br-Br bond, gaining a pair of electrons and a negative charge in the process. But the intermediate carbon-based species at the top there is different to how it was before, right? Instead of a carbocation with a positive charge on one of the carbons, we now have both of the carbons still with 4 bonds, but we have this strange situation where the bromine has 2 bonds to it and a positive charge. This is given the name the bromonium species, and hence the name for this other version of the mechanism. Now, just like the carbocation, the bromonium species is also not stable and is very prone to further attack. And the attack will come again from a bromide ion. It doesn't have to be a bromide, the bromide ion produced from the Br2 molecule that attacked this alkene group, but obviously in a reaction mixture this will be going on millions and millions of times. So a nearby bromide ion produced in one of the first mechanism steps can attack using its lone pair, like before, but to form a bond between it and one of the carbon atoms. Of course, that would put the carbon atom up to 5 bonds, and so an existing bond, the one to the bromine, can break with the electrons from that bond going onto the bromine. If you think about it in terms of charge, where with the top bromine, the bromide at the top, where the arrow's moving away from it, that will take negative charge away. So where it was a bromide negative ion, it will lose that negative charge. The carbon involved here is both having an arrow coming towards it and going away from it, so its charge will stay unchanged. And the bromine at the bottom, the bromonium with its positive charge, where the arrow is showing electrons moving towards it, negative charge is going to be moving in and cancelling out that positive charge, leaving it uncharged as well. And so we end up once again with the expected addition product of the reaction of an alkene with Br2, the double bond turned to a single bond and 1 bromine attached at each end. As a final consideration for this topic, we just need to look at some evidence that supports these mechanisms. The sceptical amongst you might be thinking to yourself, well, that's a lovely story. Somebody's been very imaginative coming up with a possibility of how this reaction could happen. But you can't see this stuff, so I mean, can we really know? And of course, all good scientific theories you need to be able to test them and look at the evidence, see if the evidence supports the theory. So we're just going to look at one simple bit of evidence that you need to know, and that is to imagine carrying out the reaction with some other negative ions present. So for instance, we react our alkene with bromine, just as before, but we do it in a solution with hydroxide ions present, let's say from sodium hydroxide, perhaps a reasonably high concentration of them. So when we get to this intermediate, the alkene group, the pi bond pair of electrons has reacted with the delta plus bromine, making a bond between one of the alkene carbons and the bromine, and leaving this carbocation, this positively charged carbon. It would make sense that any negative ion could attack that if it had a lone pair of electrons. It doesn't have to be the bromide ion produced by the first step in the mechanism, and certainly if there's quite a high concentration of hydroxide ions in the solution, then it's probably likely that one of them will definitely take that role. So we might expect to see the lone pair on the oxygen in the negative hydroxide ion equally capable of forming a bond with that positively charged carbon, and we'd expect to see a product like this. So now, rather than one bromine atom attached to each of the carbons that was in the alkene group, one has a bromine, but the other has an alcohol group. And this can be tested, and indeed this is what is seen to happen. So this lends support to this mechanism. Well, if this is the first time you've ever come across mechanisms and you're somebody normal, your head will probably be spinning at this point, going, wow, a lot of information, some of it made sense. Not sure I could just happily recite all of that and use it in any given context. So I would strongly encourage you to see
grab a piece of paper. Don't worry about making mistakes. See what you can jot down. See if you can start with an alkene group and a Br2 molecule, and just sketch out the steps for the carbocation route, maybe for the bromonium route as well. Use the curly arrows, think about charges, see if you can work your way from the starting materials, the alkene and the Br2 molecule, through to the product. And then, maybe speeding things up a bit, but watch the video again and check if you're right. And if not, then see what you're getting wrong, pick up on what you're missing, and have another go. And just keep at it until this starts to become something that seems fairly natural to you.